Okay, so now we introduce yet one more notion, that of symmetry, and that is going to help us spoil things like maximum choice and everything. What do we mean by symmetry? Well, we're going to we take the permutation group of A, SA as we tend to call it in algebra. We take a subgroup of that, and we're only going to look at those permutations. Fine. But if we want to make this all work, we need a little bit more. We need to look at special families of subgroups of G. We're going to, like I said, we're going to define our symmetry, and the main ingredient of that is this. You take a family of subgroups, you call it a normal filter, if what? Okay, first we get the filter axioms. If you know what they are, you will recognize them. If not, here they are. Okay, and now I'm going to regret my K for the kernel. But it's about the only time I use K for a subgroup anyway. So if I have a subgroup, if I have a member of the filter and I have a bigger subgroup, then that subgroup is in F as well. Okay, these three things define filter. And what about the normality? Well, this is what's going to be, so this is sort of the dividing line between filter and the adjective normal. If we have a member of the filter and we conjugate it, then we get another member of the filter. And what that thing is called the stabilizer of A. For every point in A, the set of permutations that fix A, that subgroup, is always a member of the filter. And, well, now why do we do all this? This is almost what was devised by Fraenkel when he was doing his permutation models for the negation of the continuum hypothesis. I'll get to his method in a moment. This was developed a little bit later to make the method just a little bit more flexible. If we have what? We have a set of atoms, we have a subgroup of its group of permutations, and we have a filter, a normal filter. Then we can define what it means for something to be symmetric. The symmetry group of some member of our universe, that's all the permutations pi that leave that thing invariant. Just like in geometry or whatever, crystallography or whatever you want to talk about, the group of transformations that leave the thing invariant, that's the symmetry group. I felt it useful for myself to actually write this down, because I could say, okay, those are all the things that leave pi, all the things that satisfy pi of x is equal to x. Yeah, but if you only say that, then you're kind of missing the point. The real point of that is that if I take the members of x and I take their images under pi, I fill up x again. That's the big point of that symmetry group. The members of the symmetry group of x permute the elements of x. Just like in geometry and everything, but I felt it useful for myself to actually realize, yes, you are permuting the elements of x. And this gets useful, again, looking into the future now, when, for example, x is a function. If x is a function, then there's all kinds of ordered pairs floating around here. But it means that if the function is invariant under pi, it means that those ordered pairs get switched around only. And that tells you something, usually with some trick, it tells you something about the values. Because the first coordinates determine the second coordinates. And so you lose a little bit of freedom, and that loss of freedom can help you actually prove a few things. Yeah?
Just a quick question. V is the entire universe, right?
V is the infinite power set operation applied to A.
Yeah.
So I wrote down in my notes, and it's not difficult. Yeah.
Sorry, just to check, on the fifth condition in the definition, Where did are the pi in S of A or in G?
Never hurts to be precise. No, we're only talking about things in G here. Very indirectly, we're looking at subgroups of G. So we should have restricted ourselves to very implicitly that was supposed to be G, but it never hurts to be explicit. Thank you. Don't do it right now. Again, save it for the train or something, or your bicycle. And it's not difficult, but it's one of those things that I feel need to be pointed out. You need to realize that kind of thing, something like this actually happens. Okay. Now, so this is the symmetry group, okay, relative to G of X. Now, suppose we have a G, suppose we have an F, and fix those for the next few minutes. This is going to be the central notion, so to speak. Suppose we have our G, suppose we have our F, then the elements whose symmetry groups are in our special filter, those are the ones we call symmetric. Okay. And what are we going to do with this? We're going to build a universe using this notion of symmetry. And what do I mean by hereditarily symmetric? This looks almost circular. X is in script V. In case you didn't realize, this is supposed to be a V. X is in script V if it is symmetric. and all its members are symmetric. But then all its members must be symmetric, and again subsets of V. That means all the members of X are symmetric as well, and all the members in all back to times immemorial. Now, like I said, this almost looks circular, but it isn't, because you can make sense of this using epsilon recursion. You can define the hereditarily symmetric names using epsilon recursion by saying, well, when am I, you could sort of make the characteristic function of the hereditarily symmetric things, you can define it by recursion. I could put that, I put that in an exercise, but I might change the exercise a little bit. Anyway, this can be made sound. Yeah.
You, like the last line on the lower board, is that not part of the definition of what a normal?
This?
Yeah.
Yeah.
Is that part of the definition, or?
Yeah. The stabilizers of all the individual elements are in the filter always.
Does that mean that the symmetry group of every axis by definition contains G, or?
Only the members of A.
Oh, yeah. Right.
Now this is basically a non-triviality condition. There is something in the filter. I mean, okay, this says there is something in the filter, but this says there is actually a lot of stuff in the filter going around, but generally you want these anyway. Because, why do we want these? Well, the members of A are symmetric by definition, so they are in this class V. One of the reasons for this very last line is to make sure that the atoms are in the model. And of course, A is a member of the model. Why? Because its symmetry group is the whole of G, and all its members are symmetric. The empty set is hereditarily, well, okay, it's symmetric and it's hereditarily symmetric because its symmetry group is everything. We always say that every permutation leaves, when I extend it to the universe, leaves the empty set in its place. Every member of the kernel is hereditarily symmetric by induction. So there are plenty of hereditarily symmetric things, but as we will see, not everything is apparently hereditarily symmetric. Okay, that depends a little bit on the filter. I can make a model where everything is hereditarily symmetric by simply sticking the trivial subgroup in the filter. The subgroup that consists only of the neutral element, that means that every subgroup is in the filter. Well, yeah. Then everything is hereditarily symmetric and nothing exciting happens. So the exciting stuff happens is when we shrink the G a little bit, or the filter. Well, you know, the G could be big, but the filter should not be too big, because otherwise we don't get anything interesting. And it should not be too small, because otherwise we only get the kernel. And maybe just the atoms, and that's about it. So we have to, choosing the right G and choosing the right F, that's an art. And we call V a permutation model. Why? Well, because it's made using permutations. And it is a model. This is all fine and dandy. I can write down this V, but Does it do anything for us? Well, as you just noticed, let's not confuse the issue. I'll just use this for the kernel. The whole kernel is a subset, is a subclass of V. So V does contain lots of stuff. But the big theorem V is a transitive model of ZFA, where transitive, the notion of transitive has been modified so as to exclude strange behavior of the atoms. So for all the sets, the element of relation is transitive. I'm not going to prove this in full detail, but I just want to indicate a few things just to show you what is going on most of the time. Well, it's transitive by the way we defined it. We simply put everything on top of each other, and we left the atoms at the bottom, but above the atoms and in the kernel everything is transitive. For example, let's make life not too difficult. Suppose I have 2 points in V, then I need to satisfy the pairing axiom. Now, how do you check the pairing axiom in this particular model? Well, easy. The element of relation is the element of relation. We know that the pair, the unordered pair x, y, lives in V. So all we need to do is show that the pair actually lives in script V. Because there's only one possible unordered pair of x and y anyway, and if we just show that it is a member of that thing, fine, we have our ordered pair. And the idea, of course, is that how do you check all these things? You check them by checking the symmetry groups, whether they are in the filter. Well, yeah, this is in the filter, this is in the filter, so this is in the filter. And why do we have this inclusion? Well, if pi doesn't move x and if pi doesn't move y, then it doesn't do anything to this. By the way, this is possibly strict inclusion, because there might be permutations that flip x and y. So there might be more here, but we don't care. We have this inclusion done. Because why is it, okay, this is symmetric. Is it a subset of V? Yes. Because x and y were from V. And so by the recursive definition, it's hereditarily symmetric. Here's another one. The union axiom. Well, again, if you want to check the union axiom, the best thing to do is to check that the union that you already have is in your subclass again. Because then the union is there. And again, okay, this takes maybe a little bit more thinking right now. So let us assume that pi is in the symmetry group of X. Now, okay, union X, that's the short definition, but what is pi of the union of X? Well, by epsilon isomorphism, that's the union of all the pi y's. Yes, but pi permutes the members of y, and that's it. And again, there's probably strict inclusion here because many permutations might simply move some elements of the union around while spoiling the members of X. And this is how it goes all the time. I'll leave that for you to figure out, that if you take the symmetry group of X, then it's a subgroup of the symmetry group of the power set of X. And again, it's all you need to know is that all the members of X are being pushed around, and also all the subsets are being pushed around. And that's roughly it. How would you do comprehension or separation, or how you want to phrase that? So that, I'm not quite sure how Benedict formulated this, but I'll take the formulation I have in my head, and it's equivalent to some extent. Okay, this is roughly what comprehension looks like. You have a formula in the language of set theory with two free variables. You can substitute something for one free variable and use it as a parameter in your definition. And then you look, oh, wait a minute. Then you look at all the members of X. X is the given set that satisfy that formula with the parameter in it, and the axiom says that's a set. Now, what do we know? What do we know? Well, if we have the P and the X, then the set Y that we're looking for happens to be in the big universe V, because our universe V satisfied the axioms. And now all you have to show is, now show that y is in V and that it's also a subset of V, but that will follow by looking at because x is in V, so all the members of x are in V. That means all the members of y are in V as well. So that is not the big thing. And now, guess what? If you look closely and you look at all the definitions and you look at the point that I made in the previous hour about permutations preserving formulas, then you will find that if you have a permutation that leaves P invariant and X invariant, then you're going to stick the pi in the whole formula. Well, nothing's going to change except that you're going to get the y, and well, you get the same y because pi of x is x and pi of p is p, and nothing exciting happens. But again, try and write this down for yourself. Just follow the rules line by line. Say, well, okay, does this happen? Does this happen? Does this happen? Does this? Yes. Oh, it's in V. But for all the axioms, and I'm going to leave the rest of the axioms to you, just to practice, all the verifications come down to something like this. You have a few parameters, finitely many sets, you have your formula, and the resulting object, its symmetry group is bigger than the intersection of the 5, 6 that you were starting out with. And then basically it's always just algebra or simply checking that things are the same all the time. Okay, so how much time do we have? I'll take a shortcut, and I'll come back to that shortcut next time. Okay, so we take an infinite, countably infinite, for all I care, set of atoms. We take the full permutation group. We don't care. And F and we're going to take the smallest possible normal filter. Remember, we had to have a filter and we had to have all those stabilizers of the 1-point sets in them. Well, if I take a finite set, then this is just the intersection of the stabilizers of the individual points. So I have the stabilizers, I take their finite intersections, And then I take only the subgroups that are bigger than some of those. So when is a subgroup in F? If and only if it contains one of those fixed subgroups for a finite setting, E. Okay, and so this is, we look at VGF. So what do we have there? We have our, we have the kernel in there, and we have our set A in there, and all the atoms are in there as well. Oh, I forgot. Well, actually, no, I don't need. Why? Well, if it did,
What's S?
pardon?
The power set engine of S.
Oh, well, that should be the empty set, the kernel, right. Very good. So we get an ordinal, and the ordinals are in the kernel, and we get an isomorphism. Notice we don't need choice for that, because that was the whole point of proving it without choice, so that you had some things without the axiom of choice to work with. Okie-doke. Okay. So suppose, no, not suppose, F is a member. If this is a member of the script V, then this F is going to be a member of the script V as well, because it's constructed using a formula from the well order. Okay. Take a permutation from the symmetry group of F. Now look at A. Look at the point in A. The ordered pair A, FA belongs to F. Okay, so the ordered pair pi A, pi F of A belongs to pi of F, which happens to be F. Because pi came from the symmetry group of F. What can we say about this point? What's the value here?
It's just FA because it's in the kernel.
Okay. Anybody?
F is an isomorphism, so
Pardon?
F is an isomorphism to pi of A equals A.
Whoa, wait a minute. A was arbitrary. Apparently, pi is the identity. So, what do we get?
Our filters trivial. Our filters like the trivial filter from the maximum.
A bit louder?
Our filter is now the maximum filter. Which,
Yeah. You could just say we have a contradiction because this is way bigger than just the identity map. We get a contradiction because this big subgroup should apparently be a subset of this tiny little subgroup, which it isn't, because if I have a finite subset of an infinite set, I can flip a few points outside that set around and still apparently keep F in its place. Well, there you have it, a set without a well order. Okay, so we'll have a short break and I'll say a few things about the homework exercises. Next time, I'll get to you in a moment. Next time we'll, like I said, this was a shortcut. There is a step between the filters and this application here that has to do with ideals, and it's actually in my notes, so you can read ahead if you want to. I'll scan them tomorrow. But there is lots of flexibility in here, and we can show that all kinds of implications that we get under the axiom of choice cannot be proven without it. I think Benedict talked about Dedekind finite sets and finite sets. Well, actually, A is Dedekind finite, but it's infinite. Think about that. So without choice, there is no proving that implication. Yeah.
I was just wondering, this proof really hinges on like finding the set E, right? That we like didn't really spell out how to do that. Is that just like our shortcut, or is it?
No, that's simply that was that happened here.
Oh yeah.
This is a binary relation on A. If that is a member of V, then I construct F from it. F is a member of V, and that simply says there must be one of those E's.
Yeah.
It doesn't say which one, it just says there is one. That's it. That's the other point. There will be a model, and I hope I can get to it, where actually sort of those sets E are more or less uniquely defined from the set that you're talking about. So in that case, you could sort of reconstruct the E from the set. But in this case, that wasn't necessary. Just, there is a finite set that determines F, and that's where the contradiction comes from. Okay, that's it. Let's say wait a minute. At 4 o'clock, I'll talk about the rest of the stuff. The homework that you just handed in. So I have to sort of see what the homework, even though I